Welcome back to Advanced Python. Today we're going to be talking about blockchains. So you've probably been hearing about blockchains forever, but no one's really explaining what a blockchain is. So all a blockchain is a distributed ledger technology. So literally what this means is that a blockchain is a database that is a chain of blocks where each block contains a set of transactions, and each of those transactions has a hash or a unique identifier that we call a hashing function. And so each of those blocks has the hash that is derived from the previous block. Okay, so it's building on each other and creating an unbreakable chain of blocks. So let's look at this as an image. So let's say we're working with Bitcoin. Bitcoin is a cryptocurrency technology that allows you to transfer money back and forth between users. So let's say we have a person that we want to do a transaction with, and so that person requests a transaction on the Bitcoin network. And so when that transaction is requested, it is then authenticated, and then a block is created representing that transaction. That block is then sent to a bunch of different nodes across the network. The nodes validate the transaction. They then receive their reward for the proof of work. And then the block is added to the existing blockchain, and the update is then sent across the network, and the transaction is then complete. But really, when we're talking about cryptocurrencies like Bitcoin and Ethereum, really what we have is two people that are interacting with each other across a network, and then all the nodes in the network are verifying the transaction that is being requested, and then the money can be sent. So that's all a blockchain actually is. There's not really anything special about the block itself. The block is based off of a hashing function, which is the basic data structure that we've had for a very long time. The special part is the way the network is set up, the system that is built around that hashing function. So again, the basic data structure of a blockchain is the hash. And this type of data basically takes information in and then generates a fixed length output that we know as a hash. And this is typically a bunch of numbers and letters built on top of each other that provides a unique identifier for that piece of data. And so what this means is that if the user inputs a even slightly different piece of data than what they had originally put in, we will get a completely different hash value, because its goal is to produce a unique output that is 100% only an identifier of that transaction or of that interaction on the network. Now, these hashes are just the process of transforming any information or string of value into another value. And so this is a way of basically encoding or encrypting the data and implementing a hash table to store the original values and providing us a value that we can show to the rest of the network that represents the data without actually having to expose the entirety of the data. Now, many times when we're talking about blockchains, the big word that you hear is that it's a decentralized technology. But in actuality, there are centralized blockchains, there are decentralized blockchains, and then there are also distributed network blockchain technologies. Okay, so really quick, we're going to talk about the differences between centralized and decentralized blockchains. So a centralized blockchain is commonly known as a private or permissioned blockchain. And so basically these kind of blockchains are controlled by a single entity or a group of entities. So this is basically a private network or a private server that can be encrypted. Now, there are advantages to having a private centralized blockchain. And the biggest deal here is that it's immutable and it's transparent. And those companies or entities that are using the centralized blockchain don't have to relinquish control of their data and access to their data through a decentralized network. Another benefit is that all the transactions can be validated by a central authority. But one of the issues with having a central authority validating your transactions is that that central authority technically has the authority to roll back transactions if necessary. So if we were pretending that we have a banking app and we want to send money from place A to place B, and the central authority does not like that, the central authority can stop you from sending your money to that other person on the network. So that's a downside. But the same thing technically could happen on a decentralized network. It would just be slightly harder because it would be based on proof of stake or proof of work. And then overall, the biggest benefit of a centralized blockchain is the fact that you can have much faster transaction processing. And that's because of the centralized nature of this and the fact that we are not relying on other nodes to verify our work. We have a central authority that is in charge of verification. Now, in a decentralized blockchains, all of the nodes participate in the validation process, and these transactions are validated based on a consensus algorithm such as proof of work or proof of stake. And the reason for using these consensus algorithms is that it makes the network more resilient to attacks and less susceptible to censorship or manipulation by a third party. So it makes it more secure and more transparent because there's no intermediary required to facilitate the transactions. So the network basically stands alone and can operate on its own without some third-party human or some third-party service confirming the transactions and confirming the actions that are taking place on the network. Now, another big benefit of the decentralized blockchain is the fact that once a block has been added to the blockchain, it can never be modified or deleted. So these transactions are recorded and are permanent. They cannot be tampered with as long as it is an open access decentralized blockchain network. Now, depending on how you view that, this could be a positive because that makes the blockchain transactions transparent. So anyone on the network can see the transaction history for the entire network. But if you value your privacy or you're concerned about some third party following or tracing your activity across the network, then having your transaction history public may be a concern of yours. And then the biggest downside to a decentralized blockchain network is the fact that they are slower and less efficient because your work has to be verified by other users and other nodes in the network. So with that said, let's talk about the real world, because the fact of the matter is we likely are not going to just have decentralized blockchains or centralized blockchains. It'll be a mix of the two. And we can see this in our own banking industry in the United States. So if we look up a Bank of America patent here, what we'll see is that American banks and financial institutions have been preparing for the blockchain and for the new financial system for years now. You'll see that this application for a patent was submitted by Bank of America all the way back in 2018 and 2019. So they have been planning for this blockchain technology for 5 years now, and probably even longer than that. So let's take a look at this patent and see what Bank of America is actually planning. So this is the first page of the patent here. This patent is called Real-Time Network Settlement by Distributed Ledger System. So basically just a generic layout of how they plan for their network to function once they switch over to blockchain technology. In this first graphic here is the basic setup of the network. So essentially they're telling us that there will be an end user that has access to a computer system. That computer system will then communicate with their system through a network. That network then provides them access to their entity or their system to access their materials in real time. And that internal system is a network of machines with distributed ledgers on them that contains the blocks and a centralized database. So that centralized database contains all of their information. So what Bank of America is actually planning to do is have a centralized blockchain with access to third-party services, as we can see in this graphic 1. So those third-party services are things like decentralized services like Bitcoin and Ethereum or smart contract networks, whatever it may be. And in actuality, this Bank of America network is not just going to be directly connected to blockchain, because what's happening is the United States Federal Reserve is building another shell of a network around all of these banking networks. So this Bank of America centralized database and centralized network would be inside of the US centralized blockchain network. And then from the US centralized blockchain network, it would be able to access Bitcoin, Ethereum, Dogecoin, smart contract applications, whatever it is. So as a American citizen or even a worldwide citizen, this is probably the direction that most banking and financial institutions are going to head in. They're going to have a centralized network that contains all of your data. That centralized network will then be overseen by a government level network. And then outside of that centralized blockchain is when you will have access to your third-party applications. Now, of course, This is beneficial to us as the end user because we have more efficient transaction speed and also technically higher level of security. So the network should be more secure. Now, the downside is we do have the potential for censorship in this network, because if we have a centralized service like our financial institutions that are controlled by the United States government or whatever world government you're interested in, that world government then can access, delete, manipulate, alter the records for the entire financial institution if they are the shell network outside of your bank network. All right, now before we move on, let's do a quick overview graphically of a centralized versus a decentralized blockchain network and even a distributed network. So in a centralized network, like what we just saw with the Bank of America application and what I expect most of the United States and other first world countries will have for their networks, we essentially have all the nodes connected to a central authority. So in the case of the US, each of these blue nodes would be an independent financial institution, and then the central white node would be the US Federal Reserve, or maybe the European Union Reserve, whatever that central bank or that central entity is that controls the distribution of money in your country. Okay, and then if we were looking at it from the bank level, this central node, the white node, would be the bank's financial systems, and then the blue nodes would be end users that had access to the ledger to interact with their banking system. Now, in a decentralized network, there's not one single authority. So these white nodes represent servers that have control over the network and the other nodes, and these servers are where our proof of work, our proof of stake, and our consensus algorithms are taking place after a transaction is sent across the network. And then these white nodes also share the updated blockchain with each other throughout the network. And then in the perfect scenario, we would all be able to use a distributed network. So in a distributed network, every single node in the network is independent and interconnected with each other. So there is no limitation to access here. Every blue node is connected to every blue node by both blue nodes and white nodes. So we have zero centralization in a distributed network in comparison to a decentralized or centralized network. So while many times people tell you that blockchains is this end-all be-all technology, in actuality what it is a new way to represent data and build networks out of that data and distribute databases. Okay, and by doing that, we can create, of course, more abstraction for the end user, but also what it does is allows us to migrate the way that we use the internet. So we used to use what is called Web 2 with distributed ledger technology. They're telling us that we're moving into what we now are calling Web 3, where everything will be distributed and accessed and decentralized, which is not actually true. It won't all be decentralized. There will still be centralized authorities that hold their own networks on servers, right? So we have things like the bank. That bank will have a centralized blockchain, but then that from that centralized blockchain or from that centralized network, you will be able to access the decentralized network, something like Bitcoin, to send money, wherever you may need to send it. And so we're going to keep it pretty simple today. We're just going to build a basic blockchain in Python, and we'll be using a library that's called Hash Library. And all Hash Library does is basically implement different hashing algorithms. So we specifically will be using SHA-256, which is basically a 256-bit encryption or hash object, excuse me. I guess I can't technically say it's encrypted, but a hash object to build today. And you're welcome to check out that documentation right here at docs.python.org. So the first step we have to do, of course, is create our block. And before we can even create our block, we need to make sure that we have our libraries downloaded. You're going to come in here and go !pip install hashlib. And honestly, I think it's going to give you an error, probably because hashlib is already installed to Google Colab. We did get an error. It looks like it exited because of a metadata generation error, but it'll still let us use this library in Colab. Now, as always, after we have our correct libraries installed, the next thing we're going to do is make our import. So we're going to import hashlib, we're going to import JSON, so JavaScript object notation, and then we're going to import time, because time is a critical element to these blocks. It's how it's tracking all of these transactions. Now, once we have our imports done, we can start defining what a block actually is. So we can define we can start to define this block right here. What does that actually represent in our blockchain? So that's the first step. And in our block class, the first thing we're going to do is define the block itself. So we're going to pass an init to it, and we're going to say this init consists of the self, the index, the timestamp, the transactions of that block, and then the previous hash. Because again, every future hash is based off of the previous hash. So they build on top of each other to chain together. And within that init, we're going to call on self.index, which will equal the index position. Self.timestamp will equal timestamp. Transactions will equal transactions. Previous hash is previous hash. And then the new hash for the next block will equal the self.calculate hash. And all of these are built into the hashlib library. So you have to use the hashlib library for this implementation. Now, after we define the init here, the next thing we're going to do is define the calculate hash function, that final hash, self.hash that you see right here. And the calculate hash function consists of two things: the data object, and data is going to be equal to the string of the index, of the time step, of the transactions, and of the previous hash. And then once we have our data object, we're going to ask for calculate hash to return a hash from the hashlib library that consists of the SHA-256 algorithm. And that will consist of the data object that we created up above, and then we're going to encode that data, and then we're going to digest it and produce our new hash for this block that we're working on. Okay, so we'll run that. There we go. If you want explanations of all of those different attributes that we just used, there's explanations down below. Now, after we have our block defined, we can figure out how to chain those blocks together. Okay, because once we have a block, those blocks are then basically appended to each other, and they're added to the existing blockchain. Okay, so we're using that previous hash to produce the next hash, and then the hash after that is produced based off of that previous hash. So in this case, we're going to define another class that'll just be called blockchain. And then of course, we're going to define the self of this class, or the init of this class, which will be self.chain, so a new object called chain, and chain is equal to create the genesis block. Now the genesis block is block 0, or block at time 0. Okay, and so that will be the next function that we need. So we're going to create the genesis block by calling on self, and then we're going to ask it to just return the block number 0 at this specific time, and then we're going to call it the genesis block and give it the number 0. Now, one of the things that we need to be able to access within our blockchain here is the latest block, because if each of the future blocks is based off of the previous blocks, we need to know what the previous block was. And so this get latest block is our way of figuring out where the previous block was. So we're going to create a function called get latest block, which will just be equal to return self.chain, and we're going to go into position -1. So we're using that integer basically to access the block and figure out what the last block's hash was. After that, we'll define add a new block. So the new block will need two parameters, the self information, and then also the object new block. That new block parameter will consist of an object called previous hash. Previous hash will be equal to self.get the latest block. So this function right here, .hash, and we will save that as the previous hash. Now, once we are ready to produce the new hash for our new block, we're going to say the new block information.hash, that object, is equal to new block.calculate hash, which we defined up above right here. And so we're calculating that hash, and then we're going to say self.chain.append, append that new block. So at that point, we're adding that new block to the chain based off of the previous block information. Now, onto each of these new blocks, we need to be able to add a transaction. Okay, so we're going to create a new function that's called add transaction, which takes two parameters, the self, of course, and then the transaction parameter. And add transaction will have one object, which will be self.get the latest block, .transactions, .append the new transaction that we are requesting, so that new parameter that we're requiring for this function. And then lastly, within our blockchain class, we need one more function that's called validate the chain. And validate the chain basically just runs through and says for I in the range of self.chain. So for each of the blocks in the chain, I want you to create a new object that's called the current block. The current block will be equal to self.chain of I. And then we're going to create another object called the previous block. Previous block will be equal to self.chain of I -1. And we're going to say if the current block hash does not equal the current block of the calculate hash function. So we're going to ask it to take the current block hash information that's stored, and then we're also going to ask it to recalculate the hash function for that current block. And if they do not equal each other, we're going to ask it to return false. And then we're going to add one more parameter or one more condition to this validation of our chain, which is going to say that if the current block has the previous hash stored, okay, and that previous hash does not equal the previous block's hash, then we need to return false. So what that's basically saying is that if the previous block hash does not equal the previous hash that was stored on the current block, so if the current block is containing the wrong information, okay, because it's building on that last hash, then we obviously do not have a valid chain, so we need to return false. And then in the case that neither of these conditions are false, then we are going to return the true value. So let's go ahead and run that. And again, there's explanations of all of those different methods down here underneath. And then lastly, what we can do is test the blockchain. So finally, we've got our block built and we've got our blockchain built, or it should be assembled. So what we're going to do is try to implement our blockchain. So we're going to start by initialing our blockchain. So we're just going to say our blockchain object. We're going to create a blockchain object, which will be equal to the blockchain class that we created up above, and it's just blank. After we've initialized the blockchain, we are going to add blocks to our chain. So step by step, we're going to go through and call on the blockchain object, and we're going to say add underscore block, which is one of the functions we built into the blockchain. And we're going to say that this block is equal to 1, and then it has to have a time parameter. So we call on time to tell us the time right now, and then we name it, which will just be transaction 1. And then if we had some specific data we needed to store after that, we can store it there. And so we'll repeat that process 3 times. Now, after we've added our blocks to our chain, basically what we want to do is just check that the data was successfully added and it prints out correctly. So all we're going to do is print the JSON, and we're going to call on json.dumps, and then we're going to say of block, and then call in a dictionary and say for block in blockchain.chain, and then we're going to indent it by 4. That's just a setting or a preference. And then the last thing we're going to ask for is the blockchain valid, and that will just be the blockchain class that we called on, or that object we created, and we're going to say validate the chain, which is the function that we added. So let's go ahead and run this and see if our blockchain implementation actually works. Okay, so here we go. So we've got index 0, which has this time step, and this is called our Genesis block. That's correct, right? We want there to be an initial block that has to build the entire chain. Okay, and that previous hash is 0, which makes sense because this is at time 0, and then this is the current Genesis block hash. Now, after our Genesis block, we add our block at index 1. That block at index 1 contains the information about the transaction, which is just transaction 1. It also contains the previous hash, which appears to match up to the Genesis block hash. You can see BB8CE3. And right here we have BB8CE3, and then we have the hash for this current block, which is D27533. And then at index 2, you see we have transaction 2. You can see that our previous hash matches. And then we've got the hash for the current block, E7030F. And then if we look at timestamp 3 or index position 3, we've got transaction 3. You can see that our previous hash matches, and we've got our current hash for this block. And then when we look to check if our validate chain was true or false, you can see, is the blockchain valid? Yes, it's valid. So the implementation of our blockchain worked. And so you can see in literally 20 minutes, maybe 30 minutes, we were able to develop our own blockchain. So while this is complicated to understand, it is not necessarily complicated to implement. It took us maybe 25 to 50 lines of code to build our own blockchain that we could host on a centralized blockchain network and store our own information. So we created a distributed ledger in approximately 30 minutes. Even better than that, our JSON outputs look good. We're showing our indexes, our timestamps, our transactions, both of our hashes for each of the blocks, and the validate method confirms that the blockchain is valid. So it has not been tampered with. All of our data looks correct. So I hope that this lecture really helped you understand what blockchain is and really demystified it, because this is a technology that you can implement for yourself to create immutable ledgers and databases that allow you to protect your data in a very secure way. Now, in our next part of this series, we're going to be actually creating our own cryptocurrency and also working with some other network like Ethereum or Bitcoin to show you how to interact with those decentralized networks. And then we're also going to talk about another potential application of blockchains, which are smart contracts. So I hope you enjoyed this lesson. I hope you have a great day and an even better rest of your week, and I'll see you next time.